The ratio 1 to 1 means that it's exactly the same size as it was from the beginning. 1 divided by 1. The ratio of 1 to 2 you can think of as being 1 divided by 2. So the way to remember it here is small number in the start, small number first, equals, and it won't let me, come on, small number is an reduction in size, okay? So small number first, reducing. Large number first is the same as 2 over 1, that's the factor increase. So large number, it's an enlargement. That's usually a good rule of thumb, okay? It means that if something is 1 in my paper, it's 1 in reality, okay? If something here is 2 in my paper, it's actually 1 in reality. This is an enlargement. And 1 on my paper, it's actually 2 in reality, so I've reduced it here. So if you think of ratios instead as being sort of converted to the fraction form, I think they're a little bit easier to understand. So let's take an example here. If we have that this worm was 5 centimeters in reality, what would it be if we drew it in the ratio 1 to 2? Well, we would be halving the 5 centimeters, and we would draw it as 2.5 centimeters long. So our reduction in the ratio of 1 to 2, our worm would be 2.5 centimeters. If we were to draw the worm in the ratio 2 to 1, it's like we'd be multiplying by the factor 2 over 1, so it would be 10 centimeters. So here we're multiplying our 5 by our ratio of a half. Here we're multiplying 5 by 1. Here we're multiplying 5 by 2 over 1. So once we convert these ratios to the fraction form, it's actually really easy to work out the real length. So that's a clue onto how to do ratios. Okay, lines of symmetry are pretty good for you to actually practice with a mirror. The best thing to do is imagine that I was going to put a mirror somewhere here on this paper, and I wanted to be able to have the reflection in the mirror exactly identical as the picture. There's only one place that I could put a mirror here where the reflection would look exactly the same as the original picture. It would be straight down the middle here. If I was to look from this side into the mirror, I would actually get this reflection in the mirror in exactly the same place. Anywhere else I put the mirror, it wouldn't look the same. If I'd put the mirror here, for example, I would actually see 2 squares in the background. That wouldn't be right. If I put the mirror here, I would see this 1.5 squares and this half a square. It wouldn't be right either. I wouldn't get to see exactly the same image in the mirror wherever I put the mirror except here. Straight down that diagonal. Here. I would get a mirror image that was exactly identical as the original. So that is our line of symmetry. So what we're looking at for lines of symmetry, it's got to be an identical mirror image. We could think of it like that. So in this, if this is a perfect square, and I pretend it is, you know that it isn't very easy drawing things here. There's actually loads and loads of different places I could put the mirror. Straight down the middle here, I would get 2 lines of symmetry, a line of symmetry here. I would get the same reflection on one side as in the other. Slap bang in the middle here of my square, I would have another line of symmetry. But I could also go diagonal to diagonal. If I put the mirror here, I would again get exactly a reflection of the triangle. And I could put a mirror here, and get another triangle exactly the same here on the other side. So that my my square here has how many lines of symmetry? 1, 2, 3, 4. 4 lines of symmetry. Lines of rotation means that if I was to rotate, if I was to keep the square here at this fixed point and then just flip it over, it would still be a square, but where would the red dot be? The red dot would be now over in this corner. So this is what we call a rotation of 90 degrees. I could then rotate this square again, one more 90 degrees. I'd still have a square, but the red dot would now be down here. It's like I'm flipping the square over again. So we've got these different points of rotation. 90 degrees, and then I did another 90-degree rotation. What would happen if I had a parallelogram then? Here I've got a parallelogram. Think of a little point on the parallelogram and think, what would happen if I rotated the parallelogram 90 degrees? Well, it would go down. Let's do it in the same color. It would be down here and then upwards like this. And where would the yellow dot be now? Sort of up here. So this would be a 90-degree rotation of that parallelogram. But then if I rotated it again, another 90 degrees, I'd get back to my horizontal point. But then my little yellow dot would now be down here. So I've done a rotation of 180 degrees from the original parallelogram to get down here. This is a 180-degree rotation. The parallelogram looks the same, but it isn't. You can see where the point is down there. So that's a little bit about rotation. It has a rotation. To get this dot back to the original point, back up there, I would have to rotate it another 180 degrees to get it back to where it started. So we say that you can rotate this parallelogram, and because it takes 2 turns to get back to the original position, 2 180-degree rotations takes it back to its original position, where the yellow dot would be up in the top left-hand corner again. The square, on the other hand, to get the square back to the original position, it would take 4 rotations at 90 degrees. 4 rotations at 90 degrees to get you back to the original position. So there's a little bit about symmetry and rotation and ratios.